So how many of you have decomposed a monolith into microservices? And how many of you have created a multi-tenant microservice to eliminate the need for other microservices? Over the years, Twitter's learned a lot in this space, and we now have an API plan that we hope will scale well into the future. So today I'm going to walk through a brief history of the Twitter APIs, followed by a discussion on the goals and design of our new public API platform. And then we'll finish with a real end-to-end example of how engineers build API endpoints using OpenAPI spec, GraphQL, and Scala. So first, let's start with some history. Our journey starts 14 years ago in 2006 when Twitter launched our first public HTTP API, which was served from a single Ruby on Rails monolith, which later became known as the monorail. By 2010, we had one of the largest Ruby on Rails systems in the world, but given its growing and complex single code base, it was becoming increasingly difficult to make changes, and it was almost impossible to parallelize work among our engineering teams. It was, at this point, time for migration. And in 2012, we completed migrating our public API off of the Rails monorail and onto numerous Thrift JVM microservices, at this time fronted by a single HTTP JVM microservice named Woodstar. Now, Woodstar was instrumental in getting almost all Twitter traffic onto the JVM, but in time, it became its own smaller monolith, which was becoming increasingly difficult to change and operate. So the drums started beating once again, and it was time for yet another migration. And in 2014, we completed the second migration from a single Woodstar API service to a set of 14 HTTP microservices running on an internal JVM framework named Macaw. Now, this microservices approach enabled really fast development speeds at first, but it also resulted in a scattered and disjointed Twitter API as independent teams designed and built endpoints really quickly for their specific use cases, but they didn't coordinate. So fast forward to 2017, when the Twitter app started using some new internal-only REST and GraphQL APIs. And having internal-only REST and GraphQL APIs helped our Twitter app teams move fast and iterate quickly without having to rely exclusively on the public API, which at this point was time-consuming to change. Sorry about the extra noise, hold on. All right. So in early 2019, we started to plan for the next major version of the Twitter public API, and we knew we needed a new architecture to address the public API's slow iteration speeds and continued fragmentation. Which brings us to this year, when our new architecture started powering the public API platform, which now hosts our first API v2 endpoints. All right, so with that brief history behind us, let's now look at the goals and architecture behind our new public API platform. So for our new platform, we knew we needed a new architecture that can more easily scale with the large number of API endpoints needed to serve current and future functionality. And as part of this design process, we drafted the following goals. Our abstraction goal is to enable Twitter engineers to build on the API and focus on just the querying and mutating of the data they care about without needing to worry about the infrastructure and operations of running a production HTTP service. Our ownership goals seek to contain core and common API logic in a single place owned by a single API platform team, while also allowing non-common API components to be authored and owned by different teams. And our goal of consistency is to provide a consistent experience for external developers by relying on our API design principles to reinforce uniformity. So with the above goals in mind, we built a common platform to host all of our new Twitter API endpoints. And to operate this multi-tenant platform at scale, we knew we had to minimize endpoint-specific business logic. Otherwise, the system would quickly become yet another unmaintainable monolith. So a powerful data access layer that emphasized declarative code over imperative code was really crucial to the strategy. And as we discussed earlier, in 2017, our Twitter app started to move to an internal-only GraphQL API, and the momentum to move to GraphQL was really building throughout 2019 when migration started to happen across the company. So it was really perfect timing, and our team followed suit as we realized that the data querying needs of the public Twitter API are really similar to the needs of our Twitter and mobile desktop clients. Put another way, Twitter clients query for data and render UIs, while the public Twitter API queries for data and renders JSON. A bonus from consolidating our data querying through a single interface is that the public Twitter API can now easily deliver new Twitter features by querying for GraphQL data already being used directly by our consumer apps. All right. So with the GraphQL-based platform approach decided, we needed a multi-tenant way now for different teams to build and contribute to the overall Twitter API. And to facilitate this, we designed several pluggable platform components. And this talk will focus on resource fields and selections. Resource fields are used to create the core resources in our systems, for example, tweet resources and user resources. And selection components are used to define how to find resources, for example, tweet lookup by ID. Using these components, teams can independently own and contribute different parts of the overall Twitter API while still returning uniform representations in responses. All right, so at this point in the story, you may be curious where endpoint-specific business logic actually lives. And we offer two options here. When an endpoint's business logic can be represented in StratoQL, which is the language used by Twitter's internal data catalog system, then we only need to write a function in a Strato-hosted managed column without requiring a separate service. Otherwise, the business logic is contained in a Thrift microservice written in Scala and exposed by a Thrift Strato column. In either case, the platform provides the common HTTP needs for API endpoints, so new APIs can be released without spinning up a new HTTP service. And if an endpoint can be constructed by querying for already existing GraphQL data, or if an endpoint business logic can be implemented in StratoQL, then we can bypass almost all service owning responsibilities for that API. So now that I've discussed the history of the Twitter APIs and high-level goals and design of the platform, let's walk through an end-to-end example. The requirements from our product manager are as follows. We must handle an HTTP GET request to /2 tweets that contains a single tweet ID in the path. If the request is ill-formed, return a 400. Otherwise, return an HTTP 200 with a JSON response that has a default ID tweet field and a default text field. We must also handle an HTTP GET request to /2 tweets search recent that accepts a query, max results, and next token param. Again, if the request is ill-formed, return a 400. Otherwise, return a 200 containing a list of tweets and the next token so that customers can paginate. And similar to tweet by ID, we need to return the same standard tweet format that's used elsewhere in the Twitter API. Our requirements will need us to create a tweet resource, which has an ID and a text field that are always returned. So on screen, you could see where both of these resource fields would be defined in our common config directory. Let's first define the tweet ID field. On the top, you could see the contents of a fragment.graphql file. And this fragment is used to retrieve all the tweet data needed to render just this field. In this case, we query for the ID string field. And at the bottom of the screen, you could see the contents of the field.scala file, which is used to configure various aspects of the field. The owning team is used to determine where to send automated pages when this field is experiencing problems. Always include being set to true makes this the default field, which is always returned. And then we specify that this field should be returned in all major and minor versions of this API. Finally, we use a special path-based renderer, which lets us declaratively specify how to render this field without the need for imperative code. Now, when imperative code is needed for rendering or error handling, it will exist in this Scala file, but the platform has a goal to limit the need for imperative code wherever possible. Next, let's look at how we define the tweet.text field. Since the GraphQL and Scala files will look almost identical to the tweet.id field, let's focus this slide on the two additional files that are present. The first file is a project file, which allows different directories in Twitter's monorepo to be owned by different teams. In this case, we include a file which indicates that TweetText is owned by the API vNext developers group in Fabricator, which is the system Twitter performs its code reviews. By specifying this project level ownership, Fabricator will ensure that all changes to this directory have a shipment from at least one member of the owning team. So that's one way we're able to distribute ownership across the platform. Second file at the bottom is the slows.json file, where the field owner can define an SLO for retrieving and rendering this individual field, an SLO being a service level objective. So in that SLO, we define a 30-day service level objective. And in this case, we say that the success rate needs to be 99%. Now, this file isn't absolutely required, but if it is missing, we'll provide a default file for the platform. Okay, next up. Sorry about that. Okay, so at this point, we've defined two fields in a tweet. At the top left, you could see the GraphQL fragment for retrieving the ID string, and below it, you could see the GraphQL fragment for returning the full text field. Now, part of the platform's build process is to read through the entire config directory and then generate the fragment on the left. Now, we can now issue a single GraphQL query for that platform on the right, instead of having to request two separate GraphQL queries. And this is kind of a key to using fragments as our rendering, as our way of doing rendering reuse. And if you're familiar with React, our setup is similar to how React Relay combines individual UI fragments into larger fragments, depending on which UI components are included in a composite UI page. So next up, let's look at how we configure selections. Recall that selections are how resources are found in our APIs. And for this example, we'll implement two selections, tweet by ID and tweet by search. Okay, first let's define a selection for looking up a tweet by its ID. On the left of your screen, you could see the openapi.yaml file that defines where this selection will be exposed in our Twitter API. The version prefix variable is a placeholder that the platform fills in for whatever major version of our API is currently enabled. And the ID variable is a path parameter, which is a required string that must conform to the specified regex. On the top right, you could see the contents of the selection.graphql file, which specifies a query for retrieving tweets. And note that the required string param in the GraphQL query corresponds to the required path parameter defined in the openapi.yaml file. We then call the tweet by REST ID field in Twitter's GraphQL schema, which returns a tweet type, and then specify that we wish a platform tweet to be returned. Recall that the platform tweet is composed of all the data that's needed to render a tweet. Finally, we have the selection.scala file, which is similar to route.scala, which we just looked at, so we could skip that here. Okay, putting all the pieces together, the top row on screen shows an HTTP request for /2 tweets20 that comes into the platform, resulting in a GraphQL query named tweet by ID to be sent with a GraphQL variable. This GraphQL variable sets the ID to tweet ID 20. And then each resource field reads the GraphQL response and renders its field value, resulting in the rendered tweet seen in the below HTTP response. Next up, we need to create a selection for retrieving tweets by search. And similar to tweet lookup by ID, we define an openapi YAML file. This time it has additional typed schema validated query params. Selection.graphql is where we search for tweets using a search query. And note the place that the platform tweet fragment is in the query. That's where we expect tweets to be returned. And as a reminder, our GraphQL schema is based on our Strato data catalog system. So in this example, when we query for the matched tweets, it's actually implemented as a thrift service, in this case named ID Hunter, which takes a search query, num results, and a token as an input, and returns matched tweet IDs and a cursor as output. Finally, we have a selection.scala file, which has an optional fail-hole request method defined, and that allows us to create a more detailed HTTP 400 response based on what our thrift search service returns to us. Putting all the pieces together here, if an HTTP request for /2 tweet search recent comes into the platform with a max results value that doesn't validate against the OpenAPI spec, then no GraphQL query is issued, and we immediately return a 400 response. And now let's look at a well-formed HTTP request. This time we issue a GraphQL request with the GraphQL variables populated from the HTTP request query params. And then at the bottom, we render tweets in the standard expected format with the default ID and text fields. All right, we've successfully built 2 new API endpoints capable of selecting tweet by ID and tweet by a search query. But wait, a new requirement comes in, and our product managers now want to start exposing tweet metrics through our API. This new field will have a separate engineering team working on it and will be optionally returned only if the customer requests it. This new field will be named public metrics, and on screen you can see how this new field will be configured. As we've seen with the tweet ID and tweet text fields, we first define a GraphQL fragment to retrieve the data we need to render, and then we include a field.scala file, notably this time setting always include to false. With this new field defined, the API platform will now make this field available to any API customer that specifies that they want this optional field. Now, since this new field is optional, we'll only want to query for it when an API customer actually requests it. To do this, let's take a look at how the platform generates the tweet fragment. As you can see on the right, our API platform adds a GraphQL include directive on every part of the query associated with an optional field. And in this case, you could see the enabling of the public metrics field variable will result in these public metric fields being included. Now, some of you may be wondering why we need to use an include directive instead of just including these optional fields in our query when a customer requests them. The reason is that Twitter's GraphQL system does not allow arbitrary queries to be run in production. Instead, we utilize persisted queries, which require our API platform to submit all queries at build time in exchange for an operation ID that is then used in production. Next, let's see what a customer request looks like for this new optional field. First up is tweet by ID, and at the top of the screen, you could see an HTTP request requesting our new public metrics field. Because an optional field is now specified, we set an additional GraphQL variable named public metrics field to true, which will enable our GraphQL include directive to include the additional fields we need to query. We could skip over looking at the GraphQL response, and at the bottom, you could see the individual requested tweet now has the new public metrics data included. All right, next up, let's look at how this would work for search. Once again, the public metrics field GraphQL variable is set to true. And then below, we could see the search results with the 2 default ID and text fields, along with the optionally requested public metrics field. These examples hopefully illustrate where our API platform really shines in letting individual developers focus on specific API components, in this case, adding a new tweet field component. The platform then combines all the components together to ensure a consistent overall API. So now that we've satisfied all the product requirements, let's briefly look at how we alert and monitor our new APIs. All components in our API platform have service level objectives defined, and our platform ensures that each of these components gets automated alerts and monitoring dashboards generated for them. And on screen, you could see what a PagerDuty alert looks like for an API component that my team owns. And then from this alert, our customers can click through to a Grafana SLO dashboard, showing the status of their long-term SLO and the various errors scoped down to individual API components, seen across the last 1 hour, 6 hours, and 3-day burn windows, which is what our alerts happen to be based on. Now, I'd love to do an entire talk in just this slide, but since I lack the time to dive in much deeper, I'll quickly mention 2 things. First, since each component in our API is owned by a single team, we ensure that critical 24/7 pages are only dispatched for problems that a team controls. For example, if the tweet public metrics field starts failing, which causes the entire tweet by ID and tweet by search routes to fail, then the field owner will be paged and woken up in the middle of the night, but will never wake up the route owner, as there would be nothing actionable for the route owner to do. Secondly, for deciding on when to alert on issues, we use the multiple burn rate alerts technique from Google's excellent book titled The Site Reliability Workbook. And I'd highly recommend checking out this book to learn more about this powerful technique. In closing, thanks for joining me as we walk through a brief history of Twitter's APIs, followed by why we built the API platform, and then finished off with a handful of real-world API examples. For Twitter, this new API platform is just the start of our journey, and our work is far from done. Notably, we have many more existing endpoints to migrate and entirely new public endpoints to build. And yes, if you're keeping track, us migrating existing v11 endpoints to v2 does mean that Twitter is currently in the midst of our 3rd major API migration. So here's hoping good things really come in threes. Thank you.